Okay, good afternoon. This is AP Calculus, section 5.1. I am Mr. McCully. This is our section 5.1 presentation for integrals, and today we're going to start talking about the transcendental functions, and so non-polynomial functions. And I like this section 5, or actually the whole chapter 5, because we review a lot of the properties that we started off. So you're going to see derivatives, you're going to see quotient rule, product rule, you're going to see integrals, and they're going to be with some of these transcendental functions. And we're also going to start off with logarithms and the exponential number e, and so that's where we're going to get started. So just real quick, we're going to review the properties of logarithms. This is a review from Algebra 2. Remember that the logarithm of 1 is always equal to 0. If you have the logarithm of a product of two values, you can separate that product into the sum of two logarithms. The big one that we used in Algebra 2 and pre-calculus was you take the logarithm of an exponential function, you can take that exponent and bring it down front, which is what we did there. And this one, when we were expanding, I told you way back in Algebra 2 that we'd use it in calculus. Now we're going to use it, and it's going to really help us make our derivatives a lot easier in the simple fact that we are not going to have to do a chain and a quotient. You notice, you see here, we've got this quotient here. If it's a function on the inside, we would have the chain rule to do the derivative of whatever logarithm is, and then the chain of that, we would have to do a quotient rule on that. But by subtracting, we do the derivative on this first part, and then we do the derivative on the second part. It makes it a lot easier. Last year, we defined the natural number in terms of a limit. We said e was the limit as x goes to infinity, and this thing should really be over here. I'm not sure why it's down there. Let's see what we got here. That should be right there. At any rate, so as we go to infinity, we take this expression to the infinite power. We get closer and closer to this value e, and then we define the ln of x as the inverse of the function y equals e to the x. And that was our definition of logarithm. You know what, let's stop here and go back. Now, at the beginning of this section, there are a number of review type questions. I would suggest you do them. I'm not going to do a whole lot of examples here. If you have questions over them, we will deal with them in class. But we're going to move right into the calculus of these things. So, calculus defines ln x as the integral from 1 to x of this expression 1 over t. And so therefore the derivative of ln x is going to equal 1 over x. And then this is an example of the chain rule, where if you are taking the derivative with respect to x of the ln of some function u, then the derivative of that will be 1 over u times the derivative of whatever that function u is. So we're going to get right into some fairly simple examples, and you can see here that I'm going to say find the derivative of ln of the quantity x squared plus x, and this is an example of this chain rule form where we have an expression on the inside, and you can do it two ways. If you can see it, don't do the full substitution. I'm going to do both. I'm going to do it the substitution way, and then I'm going to talk about it in terms of the chain rule. So the first thing that I'm going to do here is I'm going to say, all right, this inner function is u, and that u is going to be x squared plus x. So the derivative with respect to x of du over dx is going to be 2x plus 1. And so if I say y equals the ln of u, then when I go to do the derivative of this with respect to x, I get dy over dx is going to equal 1 over u times du over dx. So now that I've got that, I'm just copying what I had here. Excuse me. I'm going to try and I'm fighting a cold, so we're going to try and drink a little water, keep my voice going. All right, so back to this. So now I know what my u is. I know what my du over dx is, so I'm going to replace that. So I'm just going to say it's 1 over x squared plus x, now I've replaced u, times 2x plus 1. So my final answer here, when I multiply these two fractions together, I get 2x plus 1 over x squared plus x. And that's not as neat as I would have liked it. See, it's a plus there. At any rate, so that's how we get it, doing the substitution way. Now, if you can see the composition of ln of x composed with x squared plus x, you can do it as a chain rule, and we can say, all right, you know what, let's just erase and start over. I can say that y prime is going to equal the derivative of the outside function, which is 1 over, leaving what's on the inside alone, so x squared plus x, times the derivative of what is on the inside. So the derivative of this inside piece of the function is just going to be 2x plus 1, and then we get 2x plus 1 is over x squared plus x is our final answer. So I was just skipping a step on that way, and if you see it, go ahead and do it that way. So these properties of logarithms that we talked about at the beginning, and you said, well, what are we ever going to use this for? And I said, well, we're introducing it now back in Algebra 2, so that when we get to AP Calculus, you'll have already seen it, and it'll make your life a lot easier. And this one right here, this is the one that really is going to make our lives a lot easier, because we're not going to have to do a chain rule with a quotient rule. We can simplify a little bit before we do our derivative, and that way we save ourselves a couple of steps. And right here, you'll see it. So if I do this as I did in the last particular expression where I derive what's on the inside, if I were to say let u equal x squared plus 2 over x, and then said find du over dx, do the derivative of this, well, that's a quotient. So I got to do the Heidi-ho or Hody-hi minus Heidi-ho all over ho-ho rule on that. And that makes that a mess, because now I've got to do the derivative. I got 1 over this times the derivative of that expression, which is a quotient. That makes it kind of ugly. But if I apply this rule first, I apply this expansion rule first, as it were, it makes my life a lot easier, a whole lot easier. So taking this, using that first rule, I'm going to rewrite first and say this is y equals the ln of x squared plus 2 plus the ln of just x. Now, if we do it like we did in the second way, if I want to find dy over dx, I take the derivative of this first expression, which is going to be 1 over x squared plus 2 times the derivative of this inside portion, which would just be 2x, plus, now we're just using that first derivative rule, since the derivative of ln x is just 1 over x. So I can just say it's plus 1 over x, and say my final answer is 2x over x squared plus 2 plus 1 over x. Now, this is actually fine as is. We have it in a usable form. If you want to combine your fractions, you can, and you might have to, as far as an answer goes on a standardized type test, you might have to combine it into one fraction. But for right now, in our case, this is good enough. So just leave it like that, realizing that at some point they may ask you to combine that into a single fraction. All right, and so I picked, to finish us up here, I picked a couple questions right out of the book here. Another one to try and save us a little time to show how these properties of exponents that I started off with at the beginning, where they go? There they are. I'm actually going to use this property and this property here to try and make it so I don't have to do a huge derivative. So in number 64, it asks you to find the derivative of y equals the ln of the third root of x minus 1 over x plus 1. Now, I've got the composition of really three functions. This x minus 1 over x plus 1, that's a function. The third root of something is a function, and then the ln of something is a function. So I technically have three chains here. I have three pieces, three functions that have been composed together, and then so I would have a huge chain. So what I'm going to do is I'm going to rewrite this, and I'm going to use those properties of logarithms to expand this a little bit and get it so that I can do each of those derivatives a little bit easier. So my first rewrite is I'm going to rewrite this as the ln of the quantity x minus 1 all over 3, or excuse me, that's wrong. The ln of x minus 1 over x plus 1 all to the 1/3 power, and that's what the third root is. Excuse me. And so first thing I'm going to do is I'm going to apply this first property, or this property right here. We're going to bring that 1/3 power down to the front. Bring this 1/3 power down to the front. And so I have 1/3 the ln of x minus 1 over x plus 1. And then I'm going to rewrite it one more time, so y equals, and I'm going to do the expansion like we did in the last problem. So I'm going to go 1/3, and then I'm going to put a little bracket here, and then it's the ln of x minus 1 minus the ln of x plus 1. Now, to this thing, I'm going to take the derivative of d over dx, and I get dy over dx. And so, since it's a constant, I'm just going to leave it there. Leave my constant alone. I'm multiplying by the derivative of x minus 1 is 1 over x minus 1 times the derivative of that inside piece, which would be 1. So I'm not going to write it. The derivative of x minus 1 is just 1. I'm going to leave it. Minus 1 over the no ln. The derivative of ln of x plus 1 is 1 over x plus 1 times the derivative of this inside composed function, and the derivative of x plus 1 is just 1. So again, I'm not going to write it. And if you want to distribute the 3 or the 1/3, you can. It's not a problem. It's not necessary. And you can finish off saying it's 3x minus 1 minus 1 over 3x plus 1. But really, either of these two would be fine for this particular problem. So again, when you get a harder problem with these natural logarithms, take a minute, look at those expressions, these properties of logarithms, and see if you can't simplify it a little bit and try and keep yourself from doing a bunch of those additional chains, because a lot of these functions are going to be compositions of multiple functions. All right, last one for today. Looking at number 80, and both of these two came from page 332. So in number 80, they ask us to find the equation of a tangent line at the given point, and then they want us to use a graphing utility. So see, we're back to finding the slope of a tangent line. Remember what that means. When they say find the equation of a tangent line, you should be thinking, okay, I've got some function right here, and they give me a point on this function. Now, I don't know if the equation that we're working on in 80 looks like this, but I'm trying to find the equation of this line right here. So I have to find its slope, and I have to find its y-intercept. And when we do that, we are finished. So the equation that they give us to do for number 80 is f of x is equal to the sine of 2x times the ln of x squared, and they want to figure out what the slope or what the equation of the tangent line is at the point 1, 0. Excuse me. Now, I see a product of two functions. There's a multiplication, the sine 2x, and this ln of x squared. And there's also a composition. The sine of 2x is the composition of the function sine x and 2x. And I have a composition here, ln of something, and that something is x squared. So there's a bunch of functions here. So I want to do at least a little bit to try and save myself some work. And so I'm going to use that one rule that says take this 2 and bring it down front. So I'm going to have the sine of 2x times 2 ln x. And now the derivative of this thing is just the constant 2 times 1 over x. And that simplifies it. I don't have a quotient, or excuse me, I don't have a chain there. I still have to do the product rule. And remember the product rule, and I'm reviewing it since we haven't done it in a while. If you have f of x is equal to g of x times h of x, then the first derivative of that is g of x times the first derivative of the second function h of x plus g prime of x times the derivative of the first function times the second function left alone. All right, so we're going to do that here. So f prime of x is going to be this first function left alone. So the sine of 2x times 2, the derivative of, because 2 is a constant, you leave it alone. And so the derivative of ln x we found at the beginning of this section to be just 1 over x. That's this part of that product rule. Added to, now I have to do the derivative of this. The derivative of sine is cosine of 2x times the derivative of what's inside. So the derivative of 2x is 2. And then I leave this second function alone, so 2 ln x. And so simplifying this, I've got the sine of 2x times 2 over x plus, it's going to look like 4 cosine 2x, and then ln of x. I think that looks pretty good. All right, so the slope, I got to do that now. I'm going to find the slope, and to find the slope of any tangent line on any point on the curve is to plug in the x value into the first derivative. So I get the sine of 2 times, let's see here, 2 over 1 plus 4 cosine of 2 times the ln of 1. And when I look at that particular, if we go back up here, first the ln of 1 is 0. So that makes our lives a lot easier. So this whole expression, because the ln of 1 is equal to 0, so this whole term cancels out. So I have 2 sine 2. That is the slope of my tangent line. And so we can deal with that in a couple of different ways. I think that what we're going to end up doing is, you know what? We'll just say this is the slope. We're going to say that that's the slope. And then, oops, getting ahead of myself. Sorry about that. And then we'll just use y minus y1 equals m times x minus x1. And we'll leave it like that. We won't put it as a decimal. So since y1 is 0, we can say y is equal to 2 sine 2 is the slope, and then x minus 1, and we will call that our linear equation and be done with it. And that's a usable function. Your calculator, remember this would have to, this 2 is in radians, and just to be safe, that's not a degree measure. Just trying to make sure you do that. And I think that's about it. Kept it down under 20, just right at 20 minutes. That's good. And so we got 4 examples. If you have questions, we will do it during our work days in class next week. Have a good day.